You are standing in a narrow medieval street where the upper stories lean toward one another and daylight narrows into a thin ribbon overhead. Timber presses against plaster. Roof lines dip and rise unevenly. Nothing looks new, yet nothing is collapsing. Here, buildings do not survive by accident. They survive by schedule, by inspection, by repair performed before failure spreads. You will follow the maintenance cycle that kept beams sound, roofs sealed, walls dry, and entire streets standing for generations. Medieval cities did not endure because they were built once. They endured because they were never left alone. If quiet systems like this help you rest while learning something real, you are welcome to return. Now, settle in as the first inspection begins. A householder presses a small blade into the end of a timber beam where it meets the stone base of the wall. The point sinks slightly, then stops. He withdraws it, studies the mark, and scrapes away a thin curl of softened wood before it can spread deeper. This is how the city keeps from collapsing. Not with grand rebuilding projects, but with seasonal inspection. Every structure in the street is subject to the same quiet rhythm. Winter compresses and freezes. Spring reveals swelling joints and opened cracks. Summer dries and tightens frames. Autumn prepares roofs and gutters for the next strain. The calendar governs survival more than the original builder ever did. You are standing close enough to see the joinery lines in the timber frame. Mortise and tenon joints that held firmly in autumn may have shifted slightly after months of moisture and frost. Expansion and contraction stress the wooden pegs that bind them. When thaw arrives, those joints are examined. A loosened peg is driven back into place or replaced before movement transfers strain to adjoining beams. Along the roof line, sight alone is enough to detect trouble. A ridge that dips by even a small measure suggests that snow weight has tested the rafters. No one waits for a collapse. A ladder is set, and the alignment is checked from above. If the sag is minor, reinforcement beneath may be enough. If more pronounced, the affected rafter will be supported and assessed for partial replacement later in the dry season. You notice plaster lines running vertically where timber frames meet infill. Hairline cracks are common after frost. They are not ignored. Water entering those cracks during spring rains will migrate inward, resting against structural wood. So the crack is traced, widened slightly to remove loose material, and filled with fresh lime before the next storm arrives. The repair is small, but it interrupts a chain of deterioration. At ground level, moisture collects where stone meets wood. Spring runoff saturates soil along the base of walls. Sill beams are probed carefully. If the surface flakes away too easily, decay has begun. Early removal of a small, softened section prevents the need to replace an entire length later. The inspection is deliberate and practiced. The mechanism is straightforward. Seasonal stress reveals weakness. Weakness is identified early. Early identification reduces the scale of intervention required. Instead of waiting for visible failure, the system assumes vulnerability and searches for it. You observe neighbors scanning each other's facades as they pass. A bowing upper story is noticed long before it becomes dangerous. In tightly built streets, one structure leaning outward alters load on shared walls. Informal reporting reinforces the inspection cycle. Awareness spreads faster than decay. Lease renewals often align with these reviews. A tenant responsible for roof upkeep cannot claim ignorance when sagging is visible from the street. Agreements tie habitation to maintenance. If a roof covering has thinned or plaster has fallen away, correction becomes a condition of continued occupancy. Storm seasons shape priorities. Before heavy autumn winds arrive, roof edges are examined for loosened fasteners or lifted thatch. Reinforcement occurs in advance of stress. Preventative action costs less than emergency repair. Rot detection relies on simple tools and practiced senses. A hollow sound when tapping a beam signals internal compromise. A darker stain spreading outward from a joint indicates trapped moisture. These cues are recognized because inspection is habitual. Previously repaired areas receive particular scrutiny. A scarf joint inserted 2 years ago is checked to ensure that pegs remain tight. A plaster patch applied last spring is tested for separation. Repairs are not assumed permanent, they are reassessed each cycle. You remain in the street as the pattern repeats across households. One ladder here, a small plaster mix there, a beam end trimmed and resealed. No single action is dramatic. Together they form the first layer of structural survival. The truth beneath the action is simple. Buildings endure because decay is expected and examined at predictable intervals. The calendar does not wait for a crisis, but rather anticipates it. From this vantage point, you see that nothing in the street stands by accident. Each wall and roofline remains upright because someone at the proper season pressed a blade into timber, traced a crack in plaster, or checked a ridge against the sky. You shift your focus. The roof determines whether a building remains dry enough to survive. Medieval cities treat roof maintenance as a scheduled obligation rather than an occasional repair. The material covering dictates the rhythm. Straw thatch typically lasts between 7 and 15 years, depending on exposure and quality. Reed thatch can extend beyond 20 years in favorable conditions. The difference matters because turnover schedules are calculated accordingly. Property holders track installation dates informally. They know which sections were replaced last and which approach the end of useful life. Moss accumulation is a primary indicator of water retention. Moss traps moisture against thatch fibers. In shaded areas, especially on north-facing slopes, moss grows thicker. Excessive growth shortens roof lifespan. Removal occurs manually with wooden rakes or by lifting upper layers during partial rethatching. This is done carefully to avoid disturbing intact sections. The ridgeline is particularly vulnerable. It receives direct rainfall and wind exposure. Ridge bundles often deteriorate faster than lower slopes. Replacement of ridge material can occur independently from the main roof. This staggered replacement pattern extends overall roof life without full removal. Patch-first culture dominates roof care. If a localized leak appears, only that area is opened and repaired. Entire roof replacement is avoided until the majority of covering has failed. This incremental approach reduces cost and limits disruption to interior structures. Smoke holes and chimney edges require reinforcement. Heat dries surrounding thatch unevenly, causing brittleness. Wind-driven sparks also pose risks. Around chimneys, tiles or clay layers may be inserted to protect adjacent straw. These additions are inspected during roof checks. In regions using wooden shingles, nail fatigue is monitored. Iron fasteners corrode over time, loosening attachment. Shingles lift at edges during storms if fasteners weaken. Periodic refastening prevents progressive peeling. Wind lift zones are predictable. Street-facing edges and corners exposed to prevailing winds receive more wear. Maintenance crews focus attention there first. Reinforcing edges prevents wind from working underneath layers. Full re-roofing is rare and deliberate. When it occurs, old thatch is stripped in stages. Underlying laths are inspected and replaced if rotted. Fresh bundles are layered from eave to ridge, overlapping tightly to shed water effectively. The layering technique is consistent. Lower courses support upper ones, ensuring runoff flows outward. Ladder access in narrow streets is managed carefully. Roof workers rely on angled supports that brace against opposite walls. In tightly built districts, access requires coordination with neighbors. Maintenance is individual but occurs within shared space constraints. Responsibility for roof upkeep varies. Tenants commonly maintain thatch if lease agreements specify it. Owners may supply materials while tenants provide labor. In some towns, guild regulations define obligations clearly. The division ensures that roofs are not neglected due to uncertainty. Removed thatch is not discarded without purpose. Usable straw may serve as animal bedding or insulation. Rotten sections are composted. Disposal is part of the maintenance system and prevents debris accumulation in streets. Roof lifespan management includes tracking exposure to shade and tree cover. Overhanging branches increase moisture retention. Periodic trimming reduces dampness and extends covering life. You observe that roof care is calculated. It is neither hurried nor ignored. The system assumes decay from sunlight, rain, frost, and smoke. Turnover schedules are known. Patches are layered deliberately. Ridge reinforcement is planned. The roof protects timber frames below. If neglected, interior beams absorb moisture and rot. Therefore, roof maintenance functions as the first defensive layer in the city's structural system. By managing lifespan in predictable cycles, medieval cities prevent cascading deterioration. The roof does not remain intact because it was built strongly once. It remains intact because it is partially renewed many times. Maintenance follows material limits and climate patterns. This predictable rhythm allows buildings to endure beyond the lifespan of any single layer of thatch or shingle. You see a system that keeps rain outside by treating roof covering as replaceable skin. Through scheduled inspection, patching, and staggered turnover, the uppermost layer of the city is kept functional. That function allows every lower layer to survive. Timber forms the skeleton of most medieval urban buildings. You observe that survival depends on understanding how wood behaves under constant exposure to moisture, insects, and time. Maintenance protocols address predictable weaknesses rather than unexpected failure. Fungal rot begins where moisture lingers. Beam ends embedded in masonry are especially vulnerable because water seeps along stone surfaces and rests against wood fibers. Inspection begins at these junctions. A probe is inserted into the beam end. If the tool penetrates deeply with little resistance, decay has advanced beneath the surface. Early-stage rot may be cut out and replaced locally. Advanced rot requires partial beam substitution. Insect infestation reveals itself through board dust collecting at beam bases or along floorboards. Fine powder beneath a timber indicates internal tunneling. The sound test confirms the diagnosis. When struck lightly, compromised wood produces a dull response rather than a solid tone. Maintenance does not always demand full removal. In some cases, affected sections are trimmed away and reinforced with adjoining pieces. Scarf joints allow partial beam replacement without dismantling entire frames. You observe craftsmen cutting angled joints into existing beams, inserting new timber sections that interlock mechanically. Wooden pegs secure the connection. The joint must transfer load evenly. Precision is necessary because improper alignment shifts stress elsewhere in the frame. Before a beam segment is removed, temporary supports are installed. Vertical posts or adjustable wedges carry the weight of upper stories. Floors may be partially lifted to access the affected area. The sequence is controlled. Load redistribution precedes removal. Older beams are rarely discarded entirely. Sound portions are repurposed for secondary structural roles such as floor joists or bracing. Reuse conserves material and maintains continuity within the structure. Timber supply is finite and valued. Smoke-darkened beams inside kitchens or hearthrooms often exhibit greater resistance to insects. Prolonged exposure to smoke acts as a preservative. Maintenance accounts for this difference. Beams in dry, smoky interiors may last longer than those near damp exterior walls. Water splash zones along street level require constant monitoring. Rainwater striking the ground rebounds onto lower timbers. Protective stone plinths or extended eaves reduce splash impact. Where protection is insufficient, lower frame sections are replaced more frequently. Replacement hierarchy reflects structural importance. Primary load-bearing beams receive priority. Secondary joists may tolerate minor surface decay longer if structural integrity remains intact. Assessment distinguishes between cosmetic deterioration and load compromise. Access to interior beams sometimes requires removal of floorboards. Planks are lifted carefully and labeled for reinstallation. Inspection beneath reveals joist condition and signs of moisture accumulation. Ventilation gaps are checked to ensure airflow prevents trapped dampness. Climate influences replacement frequency. In wetter regions, timber turnover accelerates. In drier climates, beams endure longer but still require periodic inspection. Maintenance systems adapt to environmental realities rather than assuming uniform conditions. Each repair leaves evidence. New wood contrasts with older surfaces. Over decades, a building becomes a record of interventions. Survival is cumulative. The structure you observe stands because compromised wood was removed before collapse spread. Timber management is deliberate. It accepts that wood decays and builds replacement into the life cycle of the frame. By addressing localized weakness with precise partial substitution, the overall skeleton remains intact without full reconstruction. Lime plaster forms the protective surface of many medieval buildings. You observe that it regulates moisture, shields timber, and provides sanitation. Its renewal follows predictable cycles tied to weather and material behavior. Cracks often appear where timber frames expand and contract. These lines are inspected visually and by touch. Fine fissures are sealed before water enters. If ignored, moisture seeps behind plaster and reaches structural wood. Early patching prevents internal decay. Lime wash is reapplied periodically as a protective coating. The mixture, composed of slaked lime and water, is brushed onto exterior surfaces during dry weather. It fills microcracks and restores brightness. The reflective surface also discourages mold growth by reducing prolonged dampness. Plaster serves as a weather shield. Its breathability allows moisture within walls to evaporate outward. This property distinguishes lime from less permeable materials. Maintenance ensures that breathability is preserved. If surface layers become too dense or contaminated, they are removed and replaced. After heavy rain seasons, inspection identifies areas where plaster has separated from laths or masonry. Hollow sounds indicate detachment. Detached sections are cut away to prevent falling fragments. Fresh plaster is applied in layers, beginning with a coarse base coat. Mixing lime putty occurs near the site. Slaked lime is combined with sand and sometimes animal hair. Hair fibers reinforce the mixture, increasing tensile strength. The ratio must be correct to prevent excessive shrinkage during curing. Patch blending requires careful feathering of edges. New plaster is smoothed into existing surfaces so water runoff remains uninterrupted. Sharp transitions create channels where moisture accumulates. Skilled application prevents this. Mold and blackening are addressed through surface cleaning and renewed lime wash. The alkaline nature of lime discourages fungal growth. Maintenance therefore functions as sanitation as well as structural protection. Sun exposure influences curing. South-facing walls dry faster and may crack if cured too quickly. Damp cloths or shading techniques moderate drying rates. Controlled curing strengthens the surface and reduces later failure. Interior plaster is maintained differently. Kitchens accumulate soot which can seal surfaces unintentionally. Periodic scraping restores permeability. Interior whitewashing brightens rooms and contributes to hygiene, reducing pests attracted to grime. Exterior plaster renewal schedules vary by climate. In wet regions, more frequent recoating is required. In arid areas, longer intervals are possible. The system adjusts accordingly. The plaster layer is not decorative alone. It regulates moisture exchange between interior and exterior environments. Without periodic renewal, water infiltrates structural timbers and accelerates decay. By maintaining the skin, the skeleton beneath remains protected. You observe that lime plaster care is quiet and repetitive. Surfaces are scraped, mixed, applied, and smoothed according to established practice. Each renewal resets the protective barrier for another cycle. The building endures because its outer layer is treated as sacrificial and renewable. Rather than expecting permanence, the city plans for continual resurfacing. Through regular inspection and targeted renewal, moisture remains controlled and structural integrity is preserved. In dense medieval streets, buildings share walls. You observe that these party walls are not simple dividers. They are structural spines carrying weight for two households at once. Maintenance of these walls requires cooperation because deterioration on one side affects the other. A party wall is typically constructed of timber framing filled with wattle and daub or of masonry in wealthier districts. Load distribution crosses property lines. Floor joists from both houses may rest within the same wall. When one building shifts, the stress transfers immediately. Inspection begins with alignment. If one facade bows outward slightly, the adjoining wall absorbs strain. You see residents checking for new cracks that run vertically between properties. These cracks indicate movement. Moisture penetration through one roof can migrate laterally into shared timbers. Maintenance requires tracing water paths carefully. Structural dependency becomes visible at upper stories where overhangs extend above the street. If one overhanging frame settles unevenly, the adjoining house experiences torsion stress. Reinforcement may require both parties to support beams temporarily while repairs occur. Coordination prevents imbalance during intervention. Legal frameworks often define responsibility. Charters in many towns specify shared liability for party walls. If one owner neglects maintenance and the wall weakens, civic authorities can compel repair. Fines may be issued when neglect endangers neighbors. Enforcement recognizes that collapse does not respect property boundaries. Disputes arise over cracks that appear gradually. Determining origin requires examination of roof runoff patterns, foundation stability, and beam alignment. If moisture from one roof drains against the shared wall, that owner may bear greater repair cost. Maintenance decisions are influenced by water behavior. Timber interlock between properties complicates replacement. Removing a beam end from a party wall requires supporting adjacent joists from both houses. Access may involve entering both interiors. Maintenance becomes a coordinated procedure rather than isolated action. Fire prevention also shapes party wall care. After urban fires, some towns require thicker masonry between homes. Brick infill may replace timber sections. Reinforcement is incremental. Each repair slightly alters the composition of the wall. Moisture migration across walls is a constant concern. If one household fails to maintain plaster, water penetrates shared frames. You observe that renewal schedules on one side influence conditions on the other. Informal pressure encourages simultaneous upkeep. Court records from some towns reveal mandated repairs when structural risk threatens public streets. Civic officials prioritize safety over private hesitation. A leaning shared wall can obstruct passage if collapse occurs. Therefore, inspection of party walls sometimes includes municipal oversight. Compensation arrangements vary. When reinforcement benefits both properties, cost may be split evenly. When one side clearly caused damage, responsibility may shift accordingly. The system depends on negotiated fairness grounded in visible evidence. Over time, a party wall accumulates layered repairs from both households. New beams intersect older sections. Masonry patches fill earlier timber voids. The structure becomes a composite record of shared maintenance decisions. You observe that survival in dense cities depends on recognizing interconnectedness. No building stands independently when walls are shared. Maintenance culture evolves to address this reality. Structural dependency encourages vigilance and communication. The wall that divides two homes also binds them structurally. Through cooperative inspection, legal enforcement, and practical reinforcement, medieval cities prevent localized decay from spreading unchecked. Shared liability becomes a stabilizing force within the urban fabric. Fire is a recurring threat in medieval cities, yet total reconstruction is rare. You observe a culture of patching rather than wholesale replacement. Fire damage repair routines focus on preserving surviving structures while reinforcing vulnerable areas. After a minor blaze, smoke staining on beams provides information. Surface charring is measured visually. If blackened wood remains firm beneath shallow char, it may stay in place. Deep charring weakens load capacity and requires trimming. Assessment determines whether removal is necessary. Partial timber removal follows a controlled process. Damaged segments are cut back to solid wood. Replacement pieces are fitted using scarf joints or lap joints. The goal is to restore strength without dismantling entire frames. Temporary supports carry load during this process. Roof segments damaged by sparks are repaired selectively. Burned thatch is removed in affected zones only. Underlying laths are inspected for heat damage. Replacement bundles are inserted seamlessly into surrounding material. Lime recoating suppresses smoke odor and seals surface cracks created by heat. Fresh plaster covers scorched wattle panels. The alkaline surface also reduces mold growth following firefighting water saturation. In districts with repeated fires, incremental material shifts occur. Timber sections may be replaced with brick infill. Chimney stacks are thickened. Hearth surrounds receive stone reinforcement. The city gradually hardens without undergoing complete redesign. Salvage culture is strong. Charred but structurally sound beams are reused in less critical positions. Nails and hardware are extracted and repurposed. Resource conservation shapes repair routines. Fire ward inspections sometimes follow significant incidents. Officials examine neighboring structures for hidden damage. Heat can weaken beams beyond visible scorch marks. Inspections identify compromised joints before failure occurs. Patchwork becomes visible over decades. A building's facade may display alternating timber and masonry segments, evidence of repeated localized repairs. Uniform appearance is less important than structural continuity. Community expectation supports rapid stabilization. When a small fire damages one home, neighbors often assist in roof patching to prevent rain infiltration. Mutual aid accelerates recovery and reduces risk of broader decay. Reinforcement around hearths becomes standard practice. Stone or tile surrounds reduce spark spread. Chimney flues are cleared of soot to lower ignition risk. Maintenance routines expand after each fire experience. Repeated patching creates layered resilience. Rather than erase damage entirely, the system integrates lessons into future repair choices. Material substitution in high-risk areas strengthens the structure gradually. You observe that fire does not automatically result in abandonment. Repair culture treats damage as localized and manageable. By trimming, reinforcing, recoating, and selectively replacing, buildings remain functional. Urban survival depends on absorbing fire impact without triggering widespread collapse. Through systematic inspection after incidents and controlled repair protocols, medieval cities rebuild without fully rebuilding. Structural continuity is preserved through deliberate incremental intervention. You direct your attention downward. Foundations in medieval cities are rarely deep by modern standards. Many structures rest on stone footings laid directly on compacted soil. Over time, that soil shifts. Settlement is expected. Maintenance addresses movement rather than denying it. Soil compression occurs gradually under constant load. In floodplain districts, saturated ground loses stability during wet seasons. You observe that subtle tilting of upper stories often originates below the visible frame. Doors that scrape at the top corner signal uneven settlement. Windows that resist closure indicate distortion along vertical supports. Inspection begins with alignment checks. Plumb lines are lowered from upper beams to measure deviation. Slight lean is tolerated if stable. Progressive tilt demands intervention. Residents monitor changes seasonally, especially after heavy rains. Stone footings can be adjusted incrementally. If a section sinks, the affected area may be excavated carefully from the exterior. Additional stone is inserted beneath the timber sill. This process lifts the frame slightly. Wooden wedges may be driven between sill and footing to correct minor misalignment. Lever systems assist in releveling. Long beams act as pry bars. With coordinated pressure, a sagging section is raised temporarily while support stones are repositioned. The operation requires patience. Sudden movement risks cracking upper plaster or dislodging joints. Floorboards are often removed to access underlying joists. Once exposed, joists are examined for compression or separation from sill beams. If joists have shifted due to settlement, they are reset and secured. Ventilation gaps beneath floors are cleared of debris to reduce moisture retention. Drainage shifts influence foundation stability. When water channels alter course after storms, soil erosion near footings accelerates. Maintenance includes redirecting runoff to prevent undermining. Stabilizing the ground is as important as adjusting the structure above. Long-term lean tolerance reflects practical limits. Slight asymmetry does not demand correction if load remains evenly distributed. You observe buildings that lean subtly yet remain structurally sound because settlement stabilized decades earlier. Bracing techniques counteract tilt. Diagonal braces may be inserted inside frames to resist further movement. These braces distribute weight more evenly and prevent progressive distortion. Urban density complicates foundation repair. Excavation near one building can affect adjacent structures. Therefore, adjustments are conservative. Stability of the surrounding ground must be preserved. In some regions, rubble infill beneath floors helps distribute load. Maintenance includes redistributing this infill if voids form. Compaction is restored manually. You notice that foundation maintenance operates slowly. No dramatic excavation occurs unless collapse threatens. Instead, careful measurement, incremental lifting, and reinforcement extend structural life. Acceptance of gradual movement is built into the system. Buildings are not expected to remain perfectly upright. They are expected to remain safe. Through regular observation and modest corrections, settlement becomes manageable. The endurance of upper stories depends on stable footing. By addressing soil compression, water erosion, and load redistribution methodically, medieval cities prevent foundation shift from escalating into collapse. The ground beneath each structure receives attention proportionate to its quiet influence. Water shapes maintenance priorities more than any other element. You observe that controlling runoff determines whether timber decays rapidly or survives decades. Drainage systems are simple but deliberate. Wooden gutters line roof edges in many towns. Carved channels direct water toward downspouts or projecting spouts. Inspection focuses on joints between gutter segments. Gaps allow leakage against wall surfaces. Pitch is checked to ensure water flows outward rather than pooling. Stone spouts sometimes replace wood at critical points. These protrude beyond wall surfaces to project runoff away from foundations. Erosion patterns at wall bases reveal effectiveness. If splash marks extend upward on plaster, diversion is insufficient. Street slope engineering supports drainage. Many medieval streets are crowned slightly at the center so water flows toward side channels. You observe residents clearing debris from these channels to prevent standing water near buildings. Ice expansion during winter cracks gutters and splits wooden channels. Spring inspection includes checking for separation along seams. Damaged sections are replaced before heavy rains resume. Water barrels positioned beneath eaves collect runoff intentionally. Overflow management is necessary. When barrels fill, excess water must be redirected to avoid saturating the foundation. Channels carved into the ground guide overflow away. Shared runoff disputes arise when one roof drains onto a neighboring wall. Adjustments may include extending spouts or altering gutter angle. Water management becomes a negotiated aspect of urban living. Drain trenches at ground level require clearing of leaves, straw, and refuse. Blocked trenches cause pooling that seeps into sill beams. Maintenance routines include periodic scraping and removal of sediment. Downspout chains or wooden pipes sometimes guide water vertically. These attachments are inspected for secure fastening. If detached, water cascades directly onto walls, accelerating plaster decay. Moisture at wall bases promotes rot in timber frames. Protective stone plinths reduce direct contact between wood and wet soil. Where plinths are absent, splash damage increases repair frequency. You observe that water diversion is preventative. Once moisture infiltrates structural wood, repair becomes more complex. Therefore, runoff control receives regular attention, particularly after storms. Roof angle influences water velocity. Steeper slopes shed water quickly, reducing saturation time. Maintenance includes ensuring that lower edges remain clear to allow uninterrupted flow. Public responsibility intersects with private upkeep. If street drains clog, individual maintenance efforts lose effectiveness. Civic ordinances often mandate periodic cleaning of shared drainage paths. The system recognizes water as persistent and patient. Control requires constant vigilance. By managing gutters, spouts, street channels, and overflow paths, medieval cities reduce the rate at which moisture undermines structural integrity. You observe that no single device prevents decay. It is the combined effect of roof pitch, gutter alignment, street slope, and regular clearing that protects buildings. Water remains a threat, but it is redirected consistently enough to preserve the urban fabric. Through steady attention to runoff patterns and drainage infrastructure, the city limits the influence of rain and meltwater. Timber and plaster endure because water is guided away rather than allowed to linger. You shift from materials to money. Maintenance is not only technical, it is financial and administrative. A building remains standing because someone is obligated to pay for its survival. Responsibility begins with ownership structure. In many medieval cities, tenants occupy houses owned by landlords, guilds, or ecclesiastical institutions. Lease agreements often define who maintains what. Roof coverings, interior beams, and plaster may fall under tenant care. Structural frames and foundations may remain the owner's duty. The division prevents confusion and delays. Annual rent cycles create inspection checkpoints. Before renewing a lease, the property condition is reviewed. If maintenance has been neglected, repair costs may be deducted from deposits or added to obligations. The system links structural care directly to occupancy rights. Guild-owned properties follow regulated standards. Guild statutes sometimes specify maintenance expectations for member properties. Failure to maintain a safe structure can result in fines or suspension. The reasoning is practical. Unsafe buildings damage the reputation and functionality of the trade district. Church-owned rental housing often uses similar mechanisms. Revenue from rent depends on habitability. Ecclesiastical administrators track repairs carefully to protect income streams. Maintenance becomes an economic necessity rather than optional expenditure. City authorities intervene when neglect threatens public safety. If a wall leans into a street or debris falls into public passageways, officials can issue repair mandates. Deadlines are set. If ignored, fines increase or forced repair may occur at the owner's expense. Civic power reinforces private responsibility. Repair costs vary according to material scarcity and labor availability. After storms or fires, demand for timber and lime increases. Prices rise. Owners may delay non-critical repairs until material becomes affordable again. The timing of maintenance therefore reflects market conditions. Skilled labor is compensated according to complexity. Replacing a primary beam requires greater expertise than patching plaster. Wage differences influence decisions about whether to attempt repair personally or hire professionals. Householders often perform minor maintenance themselves to reduce expenses. In some neighborhoods, collective repair pooling emerges informally. If multiple houses share drainage issues or party wall reinforcement, cost-sharing reduces individual burden. Collective funding accelerates maintenance that benefits several properties simultaneously. Eviction can occur when tenants fail to meet maintenance obligations that are clearly stated in leases. A deteriorating roof affects not only one household but adjacent ones. Owners may remove occupants who neglect responsibilities to protect the broader structure. Insurance in the modern sense is limited, but communal funds sometimes exist after widespread disaster. Contributions collected after major fires may support rebuilding of essential structures. These funds stabilize the urban economy by preventing long-term abandonment. Material reuse reduces financial strain. Salvaged timber and hardware from abandoned buildings can lower repair costs elsewhere. Economic efficiency intersects with structural maintenance. You observe that upkeep decisions are rarely emotional. They are calculated within income limits and legal frameworks. A building stands because someone calculates that repair cost is justified compared to loss of rent or fines. Deferred maintenance often signals financial stress. When plaster remains cracked or roof patches are postponed, economic pressure is visible. Over time, lack of funding can push a building toward abandonment. Therefore, the economic layer underlies every physical intervention. Urban endurance depends on predictable enforcement and clear allocation of responsibility. Without defined payment structures and legal incentives, maintenance would falter. Instead, economic systems reinforce the habit of repair. The city remains upright because financial obligations align with structural necessity. Money circulates through carpenters, plasterers, and laborers, sustaining both the built environment and the trades that preserve it. Despite structured maintenance, some buildings reach a point where repair no longer continues. You observe that abandonment is gradual and deliberate rather than sudden. Signs of deferred maintenance appear first in small details. Roof patches accumulate without full replacement. Plaster sheds in larger sections and remains unrepaired. Timber discoloration spreads along lower beams. These indicators suggest that resources or willingness to maintain have diminished. Progressive roof collapse often begins at ridge lines. Once protective covering fails widely, rain penetrates interior spaces, floorboards warp, joists absorb moisture, structural decay accelerates. Without intervention, upper stories sag inward. As timber skeletons become exposed, wattle infill drops away. Wind enters freely. The building's envelope no longer shields interior structure. At this stage, repair requires substantial investment. Some owners decide against it. Salvage stripping precedes full abandonment. Reusable beams, iron fittings, and door hardware are removed deliberately. Materials are repurposed elsewhere. The process extracts remaining value before surrender. Vacant buildings sometimes convert temporarily into storage spaces or animal shelters. Reduced load demands allow partial use even as structural integrity declines. This intermediate phase can extend for years. Street narrowing may occur when a structure collapses partially outward. Debris is cleared, but foundations remain. Adjacent buildings adjust their facades to close gaps or reinforce exposed party walls. Reused foundation stones support new construction in later decades. The original footprint influences future layouts. Even in abandonment, structural memory persists. Periods of plague or economic downturn increase abandonment rates. Reduced population lowers rental demand. Without income, maintenance halts. Entire rows may deteriorate slowly until new occupants arrive years later. Municipal orders sometimes require dismantling unsafe shells. If a building threatens collapse into a public way, authorities mandate removal. Dismantling is controlled. Salvageable components are extracted before final clearance. Urban decay patterns emerge gradually. You observe blocks where maintenance cycles have paused. Contrast between maintained and surrendered structures reveals the importance of continuous repair. Abandonment is not the failure of construction alone. It is a failure of economic support, communal oversight, or material supply. Once maintenance cycles stop, decay proceeds without interruption. Yet even surrendered buildings contribute to the system. Their materials re-enter circulation. Their foundations shape new structures. The city evolves through replacement rather than complete erasure. You observe that medieval cities remain standing overall because abandonment is localized and managed. Most buildings are maintained continuously. Those that are surrendered do not cause total collapse of the urban fabric. The system functions by accepting that some structures will exit the cycle. Survival depends on ensuring that the majority continue within it. Through seasonal inspection, roof turnover, timber replacement, plaster renewal, shared wall cooperation, fire patching, foundation adjustment, drainage control, and economic enforcement, the city sustains itself. Buildings stand not because they resist decay permanently, but because decay is answered repeatedly. When answers cease, structures return to the ground. When answers continue, they endure across generations. The last inspection is recorded. The street grows quiet again. Timber holds, plaster dries. Roof lines settle beneath the same narrow ribbon of light. These buildings did not survive because they were strong once. They survived because they remained under watch. Here in the archive, even stone depends on attention. If quiet histories like this bring you rest, you are welcome to return.